In the previous video, we defined the cross product of two vectors in R3, as well as used determinants to come up with sort of an efficient way of computing the cross product of two given vectors. In this video, we're going to focus on the properties that the cross product satisfies and look at some different problems that it helps us solve. A cross product has a variety of properties, but the main property that it has is the following, the one that we really designed or developed the cross product for. And that main property is that U cross V is orthogonal to U and V. And we really don't need to justify this property in the way that we developed the cross product, because this is, if you go back to the very beginning of the previous video, this is where we started with. We wanted a vector orthogonal to U and V, and we found what that meant. We took the dot product of a vector C with U and V individually, wrote them as equations of real numbers, solved that system, and that was our definition of the cross product. So this just follows naturally from how we developed this cross product. But this is the primary use of the cross product in multivariable calculus, is to produce a vector that is orthogonal to two given vectors. Right? So for example, let's say we wanted to do the following. Let's say we want to find a vector perpendicular to a plane, or to the plane, passing through the following 3 points. So we're going to define P to be the point -2, 1, 3. Q will be the point 4, -3, 1. And R will be the point 5, 5, 3. Right? So we want to find a vector perpendicular to the plane passing through these 3 points. So the first thing that we should really think about is, does such a plane even exist? And so this is a fact of three-dimensional geometry that we're not going to really justify, but we're going to use a lot. And that is, if I pick 3 points in 3 space, then there is a unique plane that passes through all 3 of them. And this is an analogous fact to the one in two-dimensional geometry, that if you have 2 points in the plane, there's a unique line that passes through them. Right? That fact you're probably very comfortable with. Your lack of comfortability with three-dimensional geometry is pretty natural for someone taking a course like this. But you can kind of think through it. It's not very difficult to see that any 3 points will determine a unique plane. And so what we're looking for is a vector that is perpendicular or normal to that plane. Okay. So in order to do that with the cross product, what we need to do is we need to find 2 vectors that lie entirely in this plane. And if we can do that, then we can take the cross product of those vectors to find one that is perpendicular to those vectors, and therefore perpendicular to the plane. Right, so just to kind of see the picture here, let's say I have my point P here, my point Q is over here, and my point R is down here, just as a pictorial example. And so these are all lying in the plane. I've oriented myself so that the surface that you're looking at is the plane that contains these 3 points. So I need to find some vectors in here, and so whenever I have 2 points, I know I can find a vector. So there's lots of choices here. For example, I could find the vector PQ, and I could find the vector PR. Right? Now these are not the only 2. I could find any combination of these, vector PQ, PR, QP, QR, RP, RQ. As long as I pick 2 vectors that have the same terminal point like this, then what we can do is when we take the cross product of these vectors, PR should be a vector. When we take the cross product, we will find one that is orthogonal or perpendicular to both of these, and so this will be the vector that we want. So this green vector I just drew will be PQ cross PR. And so we want that. So that is our vector that we want. So this picture tells us exactly how to solve this problem. So we need to compute vector PQ. So vector PQ, remember we take the coordinates of Q and we subtract the corresponding coordinates of P. So we have 4 minus negative 2 is 4 plus 2 is 6. We have negative 3 minus 1 is negative 4. And we have 1 minus 3 is negative 2. So vector PQ is 6, negative 4, 2. Vector PR is 5 minus negative 2, which is 7. 5 minus 1, which is 4. And 3 minus 3, which is 0. So we get PR as the vector 7, 4, 0. And so the vector that we're looking for is, we can find by looking at the cross product of PQ and PR. So if we use the determinant approach to compute this, we take ijk across the top. We take vector PQ, 6, negative 4, negative 2 as the second row, and PR, 7, 4, 0 as the third row. So now we just compute this determinant. So for the first component here, we get the I, so we have negative 4 times 0, 0, minus 4 times negative 2, so we're subtracting 8, or subtracting negative 8, so that'll be 0 plus 8 times I, minus, for the j component, we're going to have 0 minus negative 14, so 0 plus 14. And for the k component, we're going to have 24 minus negative 28, so plus 28k. All right, so it looks like we end up with the vector 8i minus 14j plus 52k. And if we want to put this in component form, we could. It's going to be 8, negative 14, and 52. Right, so this vector 8, negative 14, 52, this is a vector that is perpendicular to the plane containing the 3 points that we were given, and it works just perfectly fine as an answer. But it's not the only answer we could have picked. In fact, we can take any scalar multiple of this vector. Okay. Right, so there's lots of different options to choose from. And there's not, of course, a right answer unless you want one with a certain length. But remember that taking a scalar multiple of a vector just changes the length. And so the length of a vector has nothing to do with it being perpendicular to a plane. That is determined completely by its direction, and scalar multiplication doesn't change that direction. Right? And so we could all come up with a different answer to this by picking a different multiple of 8, negative 14, 52. Right? But the cross product is the thing that does the job here. Right? So I mentioned that the main property of the determinant was that it is orthogonal to the vectors u and v that we started with. But there are other properties of how we can use this algebraically. And just like with the dot product, this list of properties we'll come back to every once in a while and just sort of say, remember, this was something we mentioned was true about this. But this particular one, there are some things that are a little bit unusual about this. So for example, at the end of the previous video, I had you try computing a couple cross products that were related to the one that I worked out. And in particular, one of them that I had you work out was by taking the same two vectors as in the example, but doing the cross product in the opposite order. And what you hopefully observed when you did that is that u cross v is not equal to v cross u. It's actually equal to the negative of v cross u. Right? So the order in a cross product does matter, and this is very unnatural. You've been taught since third grade that multiplication is commutative, and in 98% of the cases it is. But in a couple cases it's not, and one of those cases is the cross product. Right? So the cross product is not commutative. It is what some people call anti-commutative. That is, if you flip the order of the two vectors, you get the negative of what you would have had from the original part. On the other hand, it is distributive. So if I have u cross a sum of two vectors, v plus w, this is equal to u cross v plus u cross w. So it is a distributive operation. If we have scalars involved, so if I have, say, AU cross BV, we can bring both of those scalars out front, A times B, and then just multiply the simpler cross product, U cross V, and then scale at the end, so we can kind of bring all the scalars out. So another property, we might ask what happens if we take the cross product of three different vectors. So for example, if I want to take U cross the cross product of V and W, right? This looks sort of like the start of an associative property, but it turns out that it's not quite the way that it works. It turns out that this is going to be U dot W, which is a scalar scaling multiplying V. So I'm taking V and I'm scaling it by the scalar U dot W. And I'm subtracting from that U dot V applied to the vector W. So notice there are no cross products on the right-hand side of this expression. There are two dot products, and there are two cases of scalar multiplication. So the V and the W are being multiplied by the scalars U dot W and U dot V, respectively. Right? So, in other words, a cross product is definitely not commutative. It's definitely not associative. In fact, it's really hard to write down a cross product of three vectors like this. Okay? So a much easier property to write down is that the zero vector crossed with any vector u will always be the zero vector. That's pretty easy to see. We also should consider what happens when we combine a dot product with a cross product. So for example, what if I wanted to compute u dot v cross w? Right? And it turns out that this is equal to u cross v dot w. Right? Now, you should point out here that in both cases, both sides of this equation are real numbers. Both are a vector dotted with another vector. So these are two real numbers that are being set equal. Right, and the last property we're going to talk about is one that you also hopefully kind of discovered at the end of the previous video, and that is what happens if I take a vector and I cross product it with itself. And if that is the case, then what we see is that we will get the zero vector. Right? And that will always be the case for any vector. Right? So, like I said, these properties here, some of them are expected, like the distributive property and the 0 cross u equals 0 for all u. But some of these are a little surprising. For example, that it's not commutative and it is not associative. In fact, associative doesn't totally make sense in this case. So I mentioned this, not that you should, make flashcards and memorize all of these properties, but we are going to want to use them from time to time. And so when we refer back to them, I just want you to have all of them sort of recorded somewhere in front of you, just so we can easily use them when we need them. So let's end this video with an example where we have to use these properties to answer a question. So let's suppose I had two vectors u and v, and I don't know what u and v are, but I do know that their cross product is the vector 1, 2, 3. And what I would like to do is I would like to find the value of the vector v cross the vector 2u plus 3v. Now, it might seem initially that we don't have enough information to do this. You know, if we knew u and v, we could quickly find 2u plus 3v, and then we could, if we knew v, we could take the cross product using the determinant, but we don't know anything about u and v, so computing this cross product with the definition or with the determinant is just out of the question. Right? So what we need to do is we need to rewrite this particular cross product in terms of stuff that we do understand. Right? So if we look at this, we have a vector crossed with a sum. And one of the properties that we talked about was that the cross product was distributive. So this is equal to, by the distributive property of the cross product, this is equal to v cross 2u plus v cross 3v. Now, for each of these two vectors that I'm adding together, we have a vector crossed with a scalar multiple of another vector. And so by the third property, the third bullet point in our list of properties that we had, we're able to go from taking a vector, a scalar multiple of a vector, and bringing that scalar out front. So for example, this first vector we can write as 2 times the vector v cross u. And the second, we can bring out the 3, and this will be 3 times v cross v. And so this is the third property mentioned on the previous slide. Okay. Well, in this case, I have 2, and then v cross u we know is the negative of u cross v. And so u cross v we're given is 1, 2, 3. So this will be the vector negative 1, negative 2, negative 3. And v cross v, that's a vector crossed with itself, that will be 3 times the 0 vector. Right? Or 3 times the vector 0, 0, 0. Right? And so, of course, this term is just the 0 vector, so adding that does nothing. So we get negative 2, negative 4, negative 6. Right? And this is the value of v cross 2u plus 3v.